This video is about the binomial expansion, which you've met in C2, and in C2 this number here, the n number, was a positive whole number. What we're looking at in this video is when this number here is a fractional number or a negative number. Now in C2, oops, here we go. We're using this formula here. And then the penultimate one was this. Then the last number was NCN, which is just 1, multiplied by y to the power n. Now, the work in this topic is making sure you understand different ways of working out these binomial coefficients when n is a fractional or negative number. You may have seen this in C2, you may not, but the formula for NCR is n factorial over n minus r factorial, r factorial. So, for example, if n equals 5 and r equals 2, then 5c2 is 5 factorial over 3 factorial, 2 factorial. 5 factorial over 3 factorial, 2 factorial works out to be 10, which is what you would get if you're using Pascal's triangle or simply pressing the buttons on your calculator. So let's look at this formula again, and let's look at NC1. NC1 is n factorial over n minus 1 factorial, 1 factorial. Now n factorial over n minus 1 factorial simplifies quite dramatically, because n factorial is this, n minus 1 factorial is this. I haven't bothered writing in 1, it's all times by 1, and then n minus 1 divided by n minus 1 is 1, n minus 2 divided by n minus 2 is 1, and so on, so on, and so on. So this simply simplifies to n, which is why the second term of a binomial expansion, you've always got the power there. Let's think about NC2. That's n factorial over n minus 2 factorial, 2 factorial. So it's n minus 1, n minus 2, n minus 3, and so on down to 1. 2 factorial is just 2 times 1. And then n minus 2 factorial is n minus 2, n minus 3, so on down to 1. That's 1, that's 1, all of these are 1, so you're simply left with n minus 1 over 2. Let's think about NC3. It's n factorial over n minus 3 factorial, 3 factorial, which is n minus 1, n minus 2, n minus 3, so on down to 1, all over 3 factorial, and then it's n minus 3, n minus 4, and so on down to 1. So that cancels, that cancels, that cancels, that cancels, so we're left with n minus 1, n minus 2 over 3 factorial. So what results have we got so far? We've got these results, and you can see that each term is growing. There's an n in each of them, but in this term there's an extra n minus 1. In this term there's n and n minus 1, and an extra term n minus 2. The denominators, there's a 1 factorial at the bottom here that I didn't bother writing in, 2 factorial, 3 factorial. So we can just use patterns to see that the next one's going to be this over 4 factorial, and NC5 is going to be n minus 1, n minus 2, n minus 3, n minus 4 over 5 factorial, and so on. So another way of writing this out is to say that it's x to the power n and then it's n x to the n minus 1 y, and then it's n minus 1 over 2 factorial times x to the n minus 2 y squared, just put that factorial in there, plus n minus 1 n minus 2 over 3 factorial x to the n minus 3 y cubed, and so on. And the last term is going to be y to the power n. Right, we're going to come back to that in a minute. So let's look at the patterns again. Here's the answers we've got so far. n minus 1 over 2 factorial, and so on. Now NCR, the general term, the bottom number 3 is that number there, 3 factorial, there's 3, for NC2 it's 2 factorial, so for NCR it's r factorial. Just need a bit of thinking about this. For NC3 it's n minus 2, so it's n minus 3 plus 1, so that's n minus 2. For NC2 it's n minus 2 plus 1, that's minus 1. So here it's the same. For NCR it's n minus r plus 1. So this is the general term. So we've got the first, we have the first term, which is always going to be 1, second term, third term, fourth term, and so on. NC0 is 1. So the first term is 1, second term, third term, and so on. Now, if we look at this bit here, at some point when n equals r minus 1, then this bit is going to be 0. That's why when n is a whole number, positive whole number, then the whole series converges because the top part becomes 0. That's why at the end we get NCn equal to 1, and there's no further terms. But if n is not a whole number, this part isn't going to become 0. If n is not a positive whole number, we're never going to get a 0 at the top, and the series is going to be infinite. So I'm now going to replace x by 1 and y by x to get the general binomial theorem. So instead of writing x, I'm going to write 1. Oh, I forgot to put a little n in here. Here we go. So instead of writing x, I'm going to write 1, and instead of writing y, I'm going to write x. So I get 1 plus x to the n is x to the power n. Well, x is 1. So I'm going to replace x by 1, 1 to the power n, that's 1. It's n. I've got x to the power n minus 1. X is 1. 1 to any power is 1. So it's going to be y, but I'm replacing y by x. So a little bit confusing, hopefully you're keeping up. I'm going to write out all this again, but instead of writing x, I'm going to write 1. Instead of writing y, I'm going to write x. So the next term is going to be n minus 1 over 2 factorial. X is going to be 1. 1 to any power is 1. Y is going to be x, so that's x squared. So the next term is going to be n minus 1 n minus 2 over 3 factorial, x cubed, and so on. Now this is going to be an infinite series because, as I said in the last slide, the top line is never going to be equal to 0. So this is going to be an infinite series that is going to work for any value of n, whether it's positive, negative, fractional, or whole number, whatever. And this is going to work. However, the x terms are getting bigger and bigger and bigger. It's going to be an infinite series, but the x terms are getting bigger and bigger and bigger, or the powers are getting bigger and bigger. So if x is a number bigger than 1, x squared is going to be bigger than that, x cubed is going to be bigger than that. But if x is smaller than 1 or greater than minus 1, then these numbers are going to get smaller and smaller and smaller. So if the mod x is less than 1, in other words x is between 1 and minus 1, then x squared is also going to be smaller than 1, x cubed is going to be smaller than 1, x fourth is going to be smaller than 1. These are going to be even smaller. For example, if x is 0.1, x squared is 0.01, x cubed is 0.001, and so on. So if mod x is smaller than 1, x squared, x cubed, x fourth, they get smaller and smaller numbers, so we can use the binomial expansion as a good approximation, taking a certain number of terms, just making sure that if mod x is smaller than 1, we realise that the higher powers of x will be smaller and smaller and smaller. So to sum up all the work that we've done so far in this video, for all values of n, this binomial expansion is true. It works if n is a positive whole number, so this, you could have used this in your C2 work, and now it works for negative and fractional indices as well. It's an infinite series, so it applies only when the modulus of x is less than 1, in other words x is between -1 and 1. And there we have it, the beautiful binomial theorem.